So when we study friction, there are a couple of different factors that contribute to the force that it'll take to overcome the friction between two surfaces. The nature of the two surfaces. So can you think of some examples of surfaces that would come in contact? So nature of two surfaces as they come in contact. Can you give me some examples of different surfaces that would have very different frictional coefficients? Ice and rubber, good. Give me a couple more examples. Ice and rubber are going to be very different, like slipperiness, right? Yep. Sandpaper, sticky or slippery? Sticky. Anything lubricated with oil, sticky or slippery? Slippery. So that's what we're going to do is we're going to look at two surfaces and we're going to come up with a number value for the slipperiness constant. The other thing, so that's about the nature of the two surfaces. The other thing that has an impact is the normal force. And the normal force is usually the weight of an object but normal force is always perpendicular to the contact surface. So if a surface is horizontal, the normal force is usually the weight of the object. Okay? The symbol that I just showed you, mu, is actually a ratio between forces that are parallel, that's what that means, that's parallel, to a surface divided by forces that are perpendicular. We have a name for these. Parallel forces are all the forces that try to slide the object, so the force to overcome friction. And then the perpendicular, that's where we have the normal. So force to overcome friction is the force that tries to slide the object. Normal force is usually the weight. Okay? The name for that is coefficient of friction. Now, mu is a ratio. What would the units be here for force, like the force to slide something? Give me an example of force unit. Newtons, yeah. Give me an example of a metric unit that we use for weight. Kilograms is the mass. Convert it by multiplying by meters per second, and you get same thing as this. Newtons, yeah, newtons. So what's going to happen if I have newtons divided by newtons? You get a ratio. So that's what this means, is that the units actually cancel. So if you're solving these problems and you're like analyzing your units, but you're not exactly sure if you're solving it right, and you're like, oh, I'm going to cancel, you're doing like factor label, right? And everything cancels. What did you probably solve for? Mu. If everything cancels, okay? Very kind that you laughed at that. All right. So ratio means no units. And mu is usually less than 1. Now notice I put the word usually. Mrs. Portinger came and talked to me because, and I teach it like this every year, but for some reason, last year's kids or some of last year's kids thought that when I said usually, what I meant was always. So usually less than 1. If you think about this, it would make sense. Say your mom says, hey, would you go move the couch for me? I want a vacuum under there, okay? You have two choices. Move the couch by sliding it. Is that parallel or perpendicular to the ground? Parallel. Or pick up the couch and move it. Parallel or perpendicular if you pick up the couch? To the ground? Perpendicular. Perpendicular. Why would you never even consider picking up the couch versus sliding it? Well, yeah, I always have that problem. You might be able to fit your arms around the couch. But what's going to be easier? Sliding. So if sliding is easier than the weight, then this number is smaller than this number, right? Are you with me? So if this is smaller than this, what's mu? Less than 1. So it's usually less than 1. There are, however, situations wherein mu can be greater than 1. Let's think of a wall with a block that we're like, I don't know, we're like holding it up against the wall with a stocking foot. Okay. The weight in this case, mass times gravity, is no longer the normal force, is it? Because the normal force is usually the weight, but the normal force has to be perpendicular to the surface. Now the weight is parallel to the surface. Okay? And in order to hold this up, friction, which always opposes the direction of motion, so the force to overcome friction is going to have to be equal to it. That's where we're going to end up with mu greater than 1. So can you think of any animals, insects, anything in nature that can do that can basically climb up a wall? A spider. Lots of insects. Yep. A lemur. Can lemurs really climb up a wall? I don't know. I don't know enough about lemurs. A squirrel. Yep. What else? Come on. What's this? A cat. Yes. A bear.
Yeah, they can climb.
Only certain ones. Yes, black bears. Yep. That's how you know. Like, is it like if I'm out west and I'm running away from a bear and I climb up a tree? Like, oh, am I being chased by a black bear or a grizzly bear? Well, if it follows you up the tree. Actually, I think black bears can climb trees and grizzlies just push them over. I think that's it. Huh? Stop being a smart aleck. All right. Brown bears are like in between black bears and grizzlies, right? I think. Like, don't even run from a grizzly because you're going to die anyways. Black bear, you might be able to outrun. They're the smaller ones. I think browns are in between. Yeah, they're not as aggressive, right? Give up. All right. So please note that I said usually next year, those of you who take AP Physics, usually less than 1, but yes, can you have a coefficient of friction greater than 1? You can. Those are really sticky surfaces. Gecko's feet, right? They can hold themselves up. What's interesting about things like cats and bears and lemurs is it's actually not the stickiness, unlike like Spider-Man has sticky fingers, right? It's a tensile strength issue for like cats and bears, because what are they using to stick to the surface? Right, they're using their nails. That's correct. Here's your question. Oh, this is the normal force. So like I hold this block up against the wall by pushing on it, right? That would be perpendicular. So that would be the normal force. And the weight in this case would end up being the sliding force. So they kind of reverse because I've changed the orientation of my surface. Okay, that makes sense? All right, we will take a pause in the video. This is for Amos, who's not here today. And then we'll do some, well, I'll give this a try. We'll try videotape.